3, 2, 1. Here we go. Okay. So let's take a look at another example. This one is a simple looking structure because, you know, there's no inclined member. As you can see, it used to be in the exam, you know, but a few years ago when everything was kind of tough, you know. So when you can see this, you have a problem right away because we have 1, 2, 3, don't know what direction it is, just draw it. 4 and 5 reaction. We have 5 reactions right away. But we also have the presence of the internal hinge here and the internal hinge there. So when you have the hinge, I believe that you have this with Ajahn Chulapot before. So it's the same concept. The hinge would tell you that the moment at that particular location is equal to 0. So we have, let's say, we can say in another term that we know the locations where the moment is 0. And now we know 2 locations that the moment are 0. So say we have 2 extra equations. So from these 5 reactions, you have your typical equilibrium equations, right? 3. And then plus 2 more extra equations here. So that means this is the determinate structure, okay? And you're gonna get this again in my next class, the structure analysis number 2. The way we do this is, you know, let's say we can always have a structure like this. Because this is typical. It's say maybe more difficult to build a hinge as a support in the framing system. So this is really normal. So, you know, when you look at the structure like this, you have 1, 2, 3, 4, 5, and 6 reactions. So let's say I can put the load on it. Doesn't matter what it is. And now I know if I am going to solve this, I have to go through a lot of things. Okay. So what I can do is that I can say, I'm going to assume that this is where my moment is 0. I'm going to assume that this is where my moment is 0. I'm going to assume that this is where my moment is 0. So we have 3 equilibrium equations. Now I assume the locations where my moment is 0. I have 3 additional equations. You say that I know that the moment at this location is 0, assuming so I can take advantage of my assumption and go to this location, cut the free body diagram, and solve for the unknowns. And because I now have 6 equations, just like the 6 reactions, my assumptions can turn this indeterminate structure into a determinate one. So in the similar fashion, I am giving this as the exam. Okay, so we sort of, somebody may have made the assumption for you that these 2 locations have moment equal to 0. So you now have 5 reactions, but you also have 3 plus 2 extra equations. So that would make this structure a determinate structure. Okay, so we just have to sit back and try to understand how the structure would work before we can begin to solve it. Okay, so with that said, you can look at the structure and you know that this is a hinge. So that is a hinge. So that would make this part pretty much something close to a simple beat, right? So I know that at these two locations, the moment is 0. So I can easily break my structure into 3 parts. That's the first one. Okay, with a little bit of a uniform load on it. And the second one with a hinge here and a hinge there. And the third one okay, with this uniform load and again that. But to write like that to show the direction. Okay, now when we break this, we would know that it's not going anywhere, your reaction. So we have 1, 2, 3. And because this is a hinge, you also have 1, 2 there. That's 1, 2. And also 1, 2. And that, and that, and that, and that. Okay. Can you see how we should deal with this perhaps? Now, because of this, we can easily take a look at this portion first. Do I have the name for it? I don't even have the name for it. So let's say, yeah, let's try to give it some name. Okay. A, B, C, D, E, and F. Okay, that would make it better. So let's take a look at member CD. Okay. Now you can see member CD. Okay. You can, how much is this? 4, so that's 12 meters long. Because both ends are the internal hinges, so you can easily take a sigma moment at C and D, and you know it's quick enough to realize that if you take the moment, or you don't even have to, you can use the sigma Fy because it's symmetric. But let's say sigma MC equal to 0, because that's the given condition, right? It's the internal hinge. It should give you the say we now have, what's the load, 1000 multiplied by the length, which is 12, multiplied by the moment arm, which is 6, okay, minus VD multiplied by 12 equal to 0. So it's exactly a half, right? So we know that's VD is 6,000. So that we now know 6,000. Okay. So the total load is simple enough. You can see that, you know, you have the length of 12 here. And when you take moment, one is 6, one is 12. So if that's 6,000, simple enough by inspection, that's a 6,000. Because your total load is in fact correct? Yeah, right. It's 1,000. So that's 12,000. So that's simple enough. Okay, but we cannot conclude anything about the axial load yet. But now we know the vertical load is 6,000. So it's simple enough. Okay. So from this, you can go on and say that's your first step. The second step, you may look at the free body diagram of this member if you want. Now you know that if this is a 6,000 upward, you have 6,000 downward here, right? You have that. The total load here, how much? It's like 2 meters long. So that's 2,000. Okay, and you also have this. Okay, so now but you can say I am using sigma f y, right, equal to 0. So now you know that your say R F is equal to 6,000 plus 1,000 multiplied by 2. So that's 8,000. Okay. So now we know that's 8,000. So that's the vertical forces taken care of. And the fact that you know that this is a hinge, this location, which is FED, the D, right? So you can take sigma MD equal to 0. All right. You would say that this should be half of that, but don't forget we have the presence of the 2,000. So when you take sigma MD equal to 0, now you would have the let's say the moment from that 2,000 multiplied by 1 square over 2, right? And then you have the moment from this as well, plus how much is the load? 500 multiplied by 6 square over 2 minus, let's call that HF, right? Minus HF multiplied by 6 equal to 0. Okay, and one more. That's not it. I forgot one more. We also have this presence, 8,000 multiplied by 2 equal to 0. Okay, that's more like it. So we know that in fact, HF turns out to be minus 8 33. Oops, sorry. Okay, no, not this one. Oops. 833 kilogram. Okay, the fact that it is negative, it means that my assumption of the direction is wrong. Wrong assumption of direction. Okay, that's how I write the direction in short. So in fact, HF is going this way. Funny how it's going in the same direction as the load. If you don't believe that, you should try sigma MF equal to 0 to obtain the, say, this force. Okay, what should I call it? Maybe HD. Okay, I should remove this. To obtain HD, that would solidify your belief that your H is going the same way as the uniform load. It's hard to believe, but it's true. But you see that HA now, if you do that, I'm sorry, not HA, HD is equal to 3.833 kilogram going to the right. So the total force here is 3,000. Okay, but because of the presence of this piece, what's that? This piece is sort of makes this reaction greater than 3,000, and therefore this has to go this way to maintain the equilibrium. Okay, so that's the second one down. So now let's say step number, because I'm running out of space, so let me make a little note here in this box. Step number 3, you can say that all the axial forces can be obtained. That's obtained, okay? After HD is calculated. So now you know that's that. This is 3.833, yeah. Going this way, so that's going in that way, that's going that way, that's going that way. Up until this point, now you know that this is 3.833. Then that is also going to this, that's 3.833. So now say number 4. Oops. What is that? Well, I didn't know that I got 2 pages that. Oh, it's a horrible. Can I remove this page? Okay, I'm sorry. Let's skip that. You need to care much about that. Okay. Now we have this the last one, which is the free body diagram of this piece A, B, C. Okay. Oops. Okay, that's that. Now we know this is 3.833, and if you want to be thorough, you can say no, hang on a minute. I should okay, because we have 6,000 here. I should bring this 6,000 down, so yeah, everything is complete. So okay, we have 6,000 down here, and we have the uniform load here. Now to make it really say thorough, I should say sigma fx equal to 0. So now you have this HA is equal to 3.833, right? Kilogram. So we have that because of sigma fx equal to 0. And you can also say sigma fy equal to 0. So now you have 6,000 plus 1,000 multiplied by 2, that's a uniform load. That's your RA, which is equal to 8,000. Okay, so that is 8,000. Now with that, with everything, it's time to take sigma MA equal to 0 to finally obtain the moment here. So MA should be equal to the moment from the uniform load. Okay, that's 1,000 multiplied by 2 makes it the total load, and then the half the distance to take the moment, so it's 2 squared over 2 plus 6,000. It's a rate vertical load multiplied by the distance, which is 2. Now these two creates a clockwise moment, but 3833 creates a counterclockwise moment. So it's a 3833 multiplied by the height, which is 6. Okay, so that's MA. That's again, my sign convention is wrong, so it's minus 9,000 kilogram meter. Okay, because I think that this clockwise moment is greater, but this counterclockwise moment generated by this is greater, so you need this moment. So this is the correct direction of the moment, 9,000. Okay, so now everything is completed. The rest should be a piece of cake, don't you think? Oh, we have the problems, questions. 2,000. 1,000 is the load, right? Why 2,000? Do I write 2,000? We don't have 2,000. Which one?
And EF.
Oh, this one, right? Sigma MD. Yeah, I kind of forget. Sorry, this should be 1,000. You're right. Thank you. Human error. The total load is 2,000. You should write 2,000 multiplied by 1, or 1,000 multiplied by. Oh, it's kind of crazy writing from me, right? Sigma M D equal to 0. That's 1,000. So it should be 2 squared over 2 as well, if I want to write it this way, right? Yeah, right. So I confused myself. Thank you very much. Okay. So if you have a structure up until this point, I don't think you should have any problem writing the shear force and bending moment diagram. But anyway, let's try to complete this. Okay, for the sake of our completion. Okay, let's say for member CD, because we have the hinge at both ends, this should be a piece of cake for you. But let's say, let's do it anyway. So get it out of the way first. CD, it's a simple structure with the hinge at both ends. And you have the let's change the color for fun. Okay, the uniform load, and then you have 6,000, and then 3833, 3833. So simple enough. You just close your eyes, play some calculation music, and that's your shear force and bending moment diagram with that value WL squared over 8, right? You are in the 3rd year now, must know this, right? WL squared over 8. 1,000 or 12, right? Square over 8. So that's 1800 kilogram meter. So that's CD over and done with. Okay, am I going too fast? No question. Okay, it's now let's move to which number? You can say EF. Let's bring them together like this. So okay, we have that. It's kind of difficult to, yeah, okay. And that. We have a hinge here, but we already know all the forces. That is 6,000. That is 3833. That's 8,000. And that is 833. So you have a little more job at hand to try to calculate the end moment at E, but that should be a piece of cake. So let me give it some name, okay? D, E, and F. I can just work on member EF. Okay, so I think it would be better for me if I write it like this. Okay, and that's my uniform load. Okay, so I have 833 down here. So I'll just skip 8,000. Okay, but you know, let's do it. Let's add it. Okay, so that you cannot say I did not complete my free body diagram. Okay, and I have 3833. So we can say sigma ME equal to 0. And it should be pleasing enough because everything is going clockwise. So we now have the load of 500. That's your uniform load multiplied by the length of 6. It's a total load, and the, sorry, half the distance to make that a moment plus 833 multiplied by 6. That is our ME, which is equal to 14,000 kilogram meter, and everything going clockwise. So our moment is counterclockwise. Okay. I say that you should complete your free body diagram first, but please forgive me. I think it's more painful for you to follow going back and forth for the free body diagram of every member. So let me complete the shear force and bending moment diagram right here. Okay. So I will create my diagram going to the left, going from the left to the right. Okay, so it's plus 3833 going downward. That's a downward force on the right. So it means it's a positive shear, right? You have a little bit left there, 833, and your bending moment diagram begins from negative value because it's counterclockwise on the left. So that's negative minus 14000 and goes back to 0. Okay, it's a positive area. Shear force diagram. in kilogram force, and bending moment diagram, kilogram meter. Okay. Now, this is going to be one of the questions that you may ask me in the future. So let me ask you now. How do you know that your curve, this is your curve? How do you know that, say, this is not the curve? This curve is wrong. Can you make quick notice why your curve is going in this direction rather than going up like that? Anybody knows?
The rate of change in slope is decreasing.
Oh, that's very good of you. Yeah, because if you look at the shear force diagram, it keeps going down. So eventually this one will bring you down to the negative value. So if your bending moment diagram is going with a gray line, it keeps increasing. Okay, so because the shear keeps going down, your moment diagram will eventually has to go down like that. So it's quick enough. Okay, if you make a quick say notice, you see, oh, okay, that's how my curve is going to look like. Good spot, man. Okay, so is there any question? Okay, so now I think DE should be simple enough. This is DE. Okay, I have the uniform load. And I now have the, say this is a hinge. Just to remind you that, hey, whatever you do, you know, when you come down to the hinge, that's where your moment is zero. Don't you forget that. You solve your unknowns by using the assumption that the moment at the hinge is zero. So when you do the diagram, you must not forget your assumptions, okay? So I have 3833. I have 6,000. So this is 8,000. 3833. I have the counterclockwise moment. So right here, I must have the clockwise moment of 14,000 kilogram meter. Okay, so that should be simple enough. The shear force diagram now is down the left. Oops, I'm sorry. Thought I hit that. Okay, it's getting stuck, right? So that's my shear force diagram. Negative area, minus 6,000, 8,000. Shear force diagram in kilogram force, or I could just leave F out. I wouldn't mind if you do the same. Okay, and my bending moment diagram, the negative area and such. So it's just we keep decreasing, and that's my bending moment diagram. Kilogram meter. Okay, is there any question? Last one now, folks. Last piece. Let's complete that.
Teacher,
yes.
Can you go back to the first page?
Okay.
On this one.
This is the second one. You mean this one?
Yes.
Okay.
Okay, Finish.
Okay, thank you for letting me know. Okay, so we have the business with the last one, which is this. But you know, it's going to be pretty much the same thing. We have the uniform load here. And we therefore with 3833 downward 6,000, 8,000 here, another 3833 here, and then moment. No, 9,000 kilogram meter. So no, it's pretty much the same thing. This piece will be pretty much the same as the one that we just finished, I suppose. Okay, so that's my free body diagram. It's 6,000. Oops, sorry. It's 6,000 downward. 3833 with that. So that is going to be 8,000, right? Did I write the equation for you? No, I didn't. I was a bad boy. Okay. So we have to do the sigma Fy equal to 0 a little bit, but you know, that's like simple enough. And the direction is wrong. All right, that's wrong. It's correct. So that's your shear force diagram, and the bending moment, because this one is a similar piece with the one that we just finished. So we should know that this moment is also the same, right? 1400 kilogram meter. If you wonder why, please come back and take a look at this. Okay, 1400. Maybe I should have a small calculation for you. This 1400 comes from, oh, we got that from EF, okay? But because we have it from DEF, so we already have that on DE, EF, I mean. And this piece, member BC, is pretty similar to DE, so I'm just gonna skip that, okay? Okay, and now when you look at the shear force diagram, if you start from the left, it becomes the upward force now. So with this time, we have the positive shear instead, and going down by the uniform load until we have 6,000 here. So that's 6,000. So this area is positive. Shear force diagram in kilogram force. And the bending moment diagram, if you start from the left, this is counterclockwise on the left, so it's a negative of minus 14,000, and with the positive shear area, it goes back to 0. Okay. Kilogram meter. And the last piece, may I look at it from this direction? Okay. So I now have 8,000. It should be red, right? Yeah. $8,000, and this is also 8,000, and we have 3833. We have 3833. We have this 9,000, and we also have that 14,000. It's oops, its direction should be this. Okay. All right. So simple enough for the shear force and bending moment diagram, because we have all the N forces for the member. So the shear, now if you begin from the left, it's a down and then up. So this is a negative shear, right? 3833. Shear force diagram in kilogram force, and then the bending moment diagram Don't forget that this is not a simple beam. You have moment on both ends, so your bending moment diagram should reflect that. Okay, it's clockwise on the left, so that's positive, so 9,000. And then it becomes, you know, the clockwise on the right, which by the sign convention, it becomes a negative moment. So there we go. That is minus 14,000 kilogram meter. And that's oops, bending moment diagram in kilogram meter. And that is a straight line. So it should not trouble you to calculate this because it's linear, about 2.35 meters. Okay, so that's it. Any question? You know, one more thing, if you don't have a question, you know, at this piece, you have two values for moment, the positive and the negative. But this is a positive moment, so it should, you know, bend like a positive moment, right? Like this. Don't forget that we begin with 0, it bends like this, and then that's a point of inflection where it bends back. See that? So this piece will go just like this because of the presence of this, and because you have a 0 rotation there, so this frame is generally going like that. See? That's according to our bending moment diagram, right? You have a point of inflection where the curvature changes. And from your bending moment diagram, you know the compression is on this side. So it just has to bend like this, going in that direction. And just take a look at this piece. You go to your bending moment diagram of EF. Okay, so you have that kind of bending moment diagram. And so compression is, where's compression? Where do I write? Okay, so that's a negative moment. We have the compression down here. So this one is a bit strange. One moment, please. Maybe it should go like this. It's a bit strange. I don't feel like it should go like that at all. This one should maybe like that. Okay, but okay. Let me you know, I feel funny about this, but according to the bending moment diagram, this is where the compression is. It should bend like that, but maybe the presence of that will make it funny. Okay, so that's the end of the second session. Is there any question? Okay, let's stop the recording.